much easier 2 weeks ago. Right, so before we get to the main course, we've got a little bit of entrée right here. So as you probably know, there's the world's largest particle collider running roughly 100 meters below our feet as we speak. And what is such a collider made of? The answer is magnets. Magnets like this one. Why do we need magnets in colliders? So if there's one thing I would like you to remember, one thing I would like you to take home from this visit is the fact, is the principle that charged particles bend their trajectories in a magnetic field. I'm going to talk about this principle a couple times throughout the visit, so please remember that. Now, if you want to keep running charged particles such as protons in a circle, and each time they pass around to give them a little kick, increase their energy, you need to constantly run them through a magnetic field. And for that we've got magnets like this. These are electromagnets. So they create a magnetic field by a current that's flowing through a coil. The coil, and here, needs to withstand 11,000 amperes of current. That's 11,000 times more than your usual household appliance. For that, you need a special technology. You can't run such a current through ordinary copper, ordinary conductors. That's why these guys are superconducting, and we can run such a harsh current and create very strong magnetic fields so that we can bend the particle trajectories at very high energies, because the more energetic they are, the less they want to bend. So, we need to pay a price for this awesome technology. We need to keep them in the superconducting conditions. They don't do superconducting stuff when they are at room temperatures. We need to cool them down. And we need to cool them down to as little as 1.9 Kelvin. That's some negative 271 degrees Celsius, just two degrees short of absolute zero, which is very, very cold. It's, in fact, one of the coldest places in the universe we know of. So, without much exaggeration, we've built ourselves a massive universe-scale fridge. All right, any questions? If not, right, please, off to you. Wait for me here in this room. If you could just wait here, I need to push a magic button. Right, everyone's here? Everyone's in?
Yep.
Cool. So, first of all, we're gonna talk some history, because everybody comes to CERN to learn some history, right?
Yep.
Okay, so it all started in the 40s and 50s, and especially in 1957, the first collider started to operate. First collider was commissioned. This is the synchrocyclotron that you're gonna learn a lot more about inside. Now, simultaneously with the construction and commissioning of the synchrocyclotron, they were already building a much larger machine, the proton synchrotron, which operates up until today, pre-accelerates the protons before they reach the LHC. It's one of the stages the protons go through before they are smashed against each other in the experiments. Now, as I mentioned outside, charged particles bend their trajectories in magnetic fields. And the more energetic they are, the less they want to bend. So the more energy you want to put in your collision, the larger machine you need, or the stronger magnets you need. Usually we go for both. So each subsequent machine we've built was larger and had stronger magnets to be able to keep the protons or the charged particles running in a circle at higher and higher energies. Now, if you want to go to higher energies, you need bigger toys. So that repeated itself quite a few times throughout the history. So after the constructions of the proton synchrotron in '59, we built a super proton synchrotron, very magnificent machine. You're gonna see it on the map soon. It's already pretty big, not as large as the LHC, but very much comparable in size, and was a great great tool to study physics at the time. Note that physicists are not the most creative people when naming colliders. We had proton synchrotron and super proton synchrotron. Nevertheless, the super kind of captures the idea. It was really a magnificent machine, repurposed a few times in history, most notably in the 80s, for collisions of protons, not with protons again, but with antiprotons, which are the antiparticles to protons. Now, the advantage of such collisions is that the probability that something really fun happens in that collision, which is given by quantum nature of the collision, is much higher if you collide protons with antiprotons than protons with protons. This is energy dependent, so the more you go to higher energies, the less that matters. But at the time, it was a really big step forward. It's a very technologically challenging and also very expensive, but it led to the discovery of, for instance, the carriers of the weak interaction. So you might have heard of the 4 fundamental forces of nature: the strong, weak, electromagnetic, and gravity. So the weak interaction was discovered or confirmed in collisions conducted on the super proton synchrotron. Then in the 80s, the atoms, for instance, protons are composed of quarks and gluons, so they form hadrons. It's strongly interacting particles that are not neutral. Those are hadrons. Electrons, quarks are not hadrons. Quarks make up hadrons. So quarks, for instance, are not hadrons themselves, but they hadronize into hadrons.
Some 54 elements are put together for the magnet frame. A total of 2,500 tons of steel. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so that protons can circulate unimpeded. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, a radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the synchrocyclotron is ready. And CERN's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with a target, giving scientists the opportunity to make systematic measurements. Operation of the SC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. 2 D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after 1/2 turn. Meanwhile, the radio frequency generator reverses the polarity between the two electrodes. The protons are now attracted to the opposite electrode and gain more energy. This process is repeated over and over again. Every time the protons make a half turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin. In 1957,
that is the assembly hall, the technical hall of Atlas, that has two massive shafts leading all the way down to the experimental cavern, through which shafts the individual pieces of the detector were lowered down and then assembled down there. This mural shows us Atlas in a scale of roughly 1 to 2, so the real thing is twice as large as the drawing on the wall here. In reality, it's not as beautifully colorful as it is here, but this one gives us a great opportunity to see what a typical high-energy collider experiment is made of. So, you can see different layers, different components of the detector. How it works. The white fireworky-looking thing in the center is a collision happening. So, we've got one beam of protons arriving from one end, another beam arriving from the other end, and in the very center they collide and produce all sorts of new particles. And these new particles are what we want to measure. So, first of all, as these particles diverge from the collision point, they see that red part, the red cylinder. That is a tracking detector. Tracking detector works as follows. It's got layers of active material, of active detector material, and as a charged particle passes through each layer, it leaves a little dot. And it leaves as many dots as it crosses layers, and then we can connect the dots, and get the trajectory of the particle that made the dots. This whole thing is happening in a magnetic field, our favorite. What do charged particles do in a magnetic field? They bend their trajectories. Now, they bend the less, the more energetic they are. So, particles with high momentum don't want to bend too much. Particles with lower momentum, they bend a lot. So, by the curvature of the track, we can actually measure the particle momentum. That's how we do it. The next part, the next detectors that the particles arrive to are so-called calorimeters. Those are the green and the blue cylinders. Those are devices designed to stop the particle and measure what energy it arrived with. The mechanisms are slightly different. We will talk more about them inside. I'll tell you how a calorimeter works. For now, just the information is just that they measure the energy of the particle. So now we have a momentum of the particle, we've got the energy of the particle, and we've got the direction in which the particle flew. So we've got a lot of information that we can piece together and actually tell what was happening in the collision itself, which is of the interest to us. So, usually the most interesting particles that we study don't make it to any of our detector layers. So, for instance, if you've got the famous Higgs boson or a top quark, they decay almost instantaneously the moment they are created, and they decay into some decay products. Those are the particles that we measure. So we need to measure all of them, ideally all of them, to piece together what was happening, because they carry the information about what we care about. They carry the information about the particles that decay, that produce them. There's one huge system I haven't talked about yet, and that's what makes Atlas so large. That's all the rest of it, in fact. Those are so-called muon detectors. Muons are particles that are very much like electrons, just about 200 times heavier. Otherwise, they are almost identical. Muons are usually in many of the decay chains of the particles that we want to study. That's why we need specialized detectors because muons, they don't want to interact with our color emitters. The color emitters are almost transparent for them. So that's why we have the rest of atoms to measure the muons, because they carry indeed the information about what was happening in the collision. The way the muon detectors work is very much like the tracker. Again, we've got a magnetic field created by those huge, massive coils that you see in orange on the side view and grayish on the frontal view, and they create a magnetic field that kind of wraps around the cylinder of atoms. And again, as the muon passes, it bends and it leaves dots in the various layers of the muon detectors. And then once again, we connect the dots, and we've got our muon momentum. Now, it's not as easy as it may sound. The connecting of the dots is not that simple. Imagine in a typical collision, you can have hundreds of tracks. You can have, for instance, 200 of tracks, and each track can leave you some 10, 15 dots to connect. At the end of the day, in the data you get, you only get the dots, you don't get the tracks. So you need to actually make some assumptions. You need to have a very, very smart, clever algorithms to actually find the tracks in that bunch of just the dots. This is what we call reconstruction. This is what we are running on a worldwide grid of computers, in fact. But I'll talk more about that once we get inside. Right now, I suggest we walk into the visitor center unless you've got any questions at this point. Magnetic coils that we use for the magnet systems, for the muon systems. So the ones that you would see in the grayish color in this frontal view, there's 8 of them in total, and they bend the trajectories of the muons so that we can tell their momentum. This is a fully working prototype that is equipped with all the superconducting wires, and they tested their power supplies and cooling and whatnot with this. They put it here on display. In reality, the real coils have the same dimension vertically, but are about 2 to 3 times larger horizontally. So this is a kind of a baby prototype. Right, let's go inside. Okay, everyone's in? Good. So I promised to you that I'm going to tell you how a colorimeter works. So once again, what's a colorimeter? It's a device, it's a detector designed to stop the particle that comes into it and measure its energy, the energy it rides with. And we've got a piece of colorimeter here in the floor. This is one piece, one wedge called a module. And in reality, you would have these modules assembled in a cylinder surrounding the interaction point, much like here in this picture that I may be able to bring up. Yes, so here in the very center, we've got a tracker. It's pretty tiny in this drawing. And in the center, there will be a collision, and what is now highlighted in blue would be the colorimeters. So how they work? You can see, if you look close, that they are made of alternating tiles. Black tiles and transparent tiles. There's no wonder we call it the tile colorimeter. Now, the black tiles are steel, just ordinary steel. The transparent tiles are a material called scintillator. A scintillator is a material that has a special property that if you pass charged particles through it, it's going to emit light, often even in visible spectrum. Now, the more particles, the more charge you push through a scintillator, the more light you're going to get. And you can collect your light with these optical wires that will then lead to your photomultipliers and digitize and get your readout, and then you can punch it as a signal with your computer. Now, the way it works, a few meters that direction, you've got a collision happening. Now, there's a particle arriving from that collision in this direction to our colorimeter. And sooner or later, it's gonna hit the steel tile. there it's going to hit one of the iron nuclei, and in that interaction it's going to produce a whole mess of secondary particles. It could be pions, it could be kaons, it could be whatnot. Many of these are charged, and when they pass from that steel tile into the transparent tile, into the scintillator is going to flash it. Now, these particles, after the first sort of collision, are still very energetic. They still are traveling very fast with a lot of energy. And when they hit the next steel tile, majority, if not all of them, will undergo the same interaction. They're going to hit one of the nuclei and produce its own shower of secondary particles. So now we've got even more particles entering our scintillator, and we've got even bigger flash. And this process repeats itself until all the energy of the primary particle is transformed into the energies and masses of the secondary particles, and then the shower dies out. And from the amount of light we've collected in such a shower, and from the shape of the shower, we can tell the energy of the original particle that's capable. Sometimes we can even tell what kind of particle it was. Different particles leave different signals in our accelerators, so it also helps us to identify the particles a little bit. Okay, does it make sense? Mm-hmm. Very good. There's another type of a scintillator right here. This was called tile. Different type of colorimeter. I want to say this was called the tile colorimeter. This would be a piece of the so-called liquid argon colorimeter. It works on a very similar principle, just we don't use this plastic scintillator, we use liquid argon as a scintillator. Liquid argon is a very, very much widely used material in particle physics. It has various good properties and it's pretty easy to get by. One of the properties is scintillation. Again, when you pass charged particles through liquid argon, it's going to produce a little flash. Now, so it works the same. You've got a steel plate and the particles create a shower in the steel, then you get a flash in the scintillator, and so on and so forth, the same old story again. Now, you can notice that this module is very weirdly shaped in a kind of accordion-like structure. Why is that? That is because you've got particles, you can imagine particles arriving from this direction. This is how it's actually assembled in the detector. That the particles would arrive from here. And no matter which angle they arrive with, they will always hit both the steel and the scintillator. So we ensure that the shower will happen and that the shower will be seen by the scintillator, by this geometry. Otherwise, if it was completely flat, our particle could just pass through the scintillator and we would see nothing because you can't see one particle. So that's another type of colorimeter. We've got also the tracker and the muon system I told you about, and we've got some examples of that in this display. So here on the right hand side, you've got pieces of the tracker. These bottom two ones are silicon modules, which are very finely segmented. They form something very much like a CCD chip in your camera. And when a particle passes through one of the segments, one of the pixels for instance, it will induce a signal in that pixel. And we can then tell which pixel it was. We've got a very precise information about where the hits were once we go on and connect them. On the other hand, the muon detectors here on the left hand side are pretty big, as you can see. They are nowhere near the scales of the tens of micrometers of the pixels in our tracker. They are much larger. They're like some 2.5 centimeters across and easily a few meters long. Why is that we can afford to have such a tiny hits, such a tiny dots in our tracker, but we can afford to have very large hits in our muon system? Do you have any idea why is that? It works the same way, we just connect the dots. But here the dots are much larger, seemingly, right?
Lots more humans, maybe?
Sorry?
More humans arriving down there?
It's quite the opposite, in fact. Because these detectors are very close to the interaction point. And you've got hundreds or tens or hundreds of tracks emerging from the interaction point. And the closer you are, the higher the density of the tracks per area. But as the tracks diverge, you get less and less of them crossing your detectors. And here you are easily 10 meters away from your interaction point. So you rarely get a track passing through your readout channel. And here you need to differentiate between the different tracks. So you need very tiny readout channels. And here, if a track comes, you are reasonably safely sure that it was only one track. And you still maintain quite a good precision with these. The way they work is much like a proportional counter. It's a tube filled with gas. When a muon passes, it ionizes the gas, and there's a thin wire running through the center of these tubes, and a potential difference of 3,500 volts between the wire and the wall of these tubes. So the charge that is deposited by the passing muon will then drift towards the wire, and you read it out at the end of the wire as a current spike. So that's how you record a hit with these. On average, each muon will leave you 36 hits in these tubes. So you will have, at the end of the day, 36 hits to connect. That's a lot. That's a lot more than you get in your tracker. So they are somewhat bigger, but they are a lot cheaper to produce, a lot easier to maintain, and still keep the good precision for our muon momentum measurement, which is what we care the most about. Yes?
Where are the trackers sitting in the system?
In the very center, yes, it's highlighted.
On the
In the very center around the
Yeah.
interaction point. So it's the first
source you get.
first detector that the particles kind of
Yeah.
pass through.
Okay.
Yeah, it looks pretty tiny, but it has actually the highest number of readout channels by far of the entire atlas, and also is the most expensive part of the entire detector, because it's a very delicate, very high tech, and has to be very much radiation hard, because it gets a lot of dosage from the collisions. Collisions constantly produce ionizing particles.
Yeah,
So
dot there, and then it goes into this to
Yes,
read
exactly.
out the energy.
perfect. Yes, exactly like that. So you first measure the momentum. They don't
Yeah.
really lose much energy by crossing the
Yeah.
silicon layers. It's
Yeah.
almost negligible, or it's negligible to all practicality. And then they
So
go
you have
to
your point, and then you just read like how the track of the particle goes through the calorimeter.
Yes, yes, indeed. So you measure the curvature of the track in your tracker to tell your momentum of the particle, and then it hits the colorimeter where it's stopped, and through this process I described, you get the energy of the particle, and you also know the direction of.
Yeah.
Right. Any more questions?
Are you running this 24 hours a day?
Yes. Around the
Lighting
clock.
particles out every.
So this is
Nobody's right.
this is the control room.
These guys play video games.
This is the control room of the Atlas experiment. And before you ask, yes, they can see you.
She said hello.
Yeah. So this is where the data taking is controlled from. This is where you start the data taking. This is where you operate. This is where you make sure that your detector is running well. The room is divided into several desks, and each of the desks takes care of a particular part of the detector. So the closest to us are the experts who take care of the colorimeters. In front of them, there would be the tracking people, the people who take care of the tracking system. On the very far end, we've got the people who take care of the muon systems. And in the center, we've got the so-called shift leaders who make sure that everything's running smoothly. They communicate with the LHC, and they solve problems in case they arise. Now there's one desk I haven't mentioned yet, and that is the one closer to the far end, closer to the doors. And that is a desk where the so-called trigger system is operated from. A trigger system is something I haven't told you about, but it's a very important part of our data taking. So what is a trigger system? Now imagine, as I mentioned earlier, you are getting 14 million collisions each second. So every 25 nanoseconds, you got 100 billion protons arriving from one side, 100 billion protons arriving from the other side, and then they collide, and somewhere between 30 and 70 of them will actually meet. Now, this is a lot of data. If this is happening around the clock, this is a very, very much high amount of data. Now, unfortunately, most of the time, and that's also why we need to do it so frequently, most of the time the protons don't do anything fun. They just bump off each other, they just scatter and fly different directions or miss each other altogether, and there's nothing interesting going on. And we are not interested in such collisions. We cannot afford to even read out the detector at such a rate. What we care about is a Higgs boson, is a top quark, or a rare decay of a B meson with a B quark. Something like that. We are after the more interesting things. So we don't really care about the cases when the protons just bump off each other. Now, therefore, we need to decide which of the collisions we are actually going to record and which we are going to throw away because they are not interesting. And that's where the trigger system comes in. The trigger system is something that can decide in real time, as we operate, whether we are going to keep that collision and record it or if we're going to throw it away. It's implemented in two stages. The first stage is hardware-based, so it's much like a computer program, but it's running not on a CPU as your normal program would, but on a dedicated printed circuit board. That is something very expensive to develop, but very fast, very, very fast, much faster, orders of magnitude faster than a CPU. And we need to be fast because we are getting 40 million collisions a second. So this first level takes very quick signals from the colorimeters and from the muons and kind of pieces them together and tells us whether there is some potential of something interesting happening. And also, importantly, it defines where in the detector it happened. So that later on we don't have to read out the whole thing, but only the interesting bits. Now, the decision of the first level, we call it level 1 trigger, fitting name, the decision is passed onto the next level of the trigger, which is already running on a CPU, commercial CPUs, and it's running a lightweight version of connecting the dots. We've got a fancy word for that, we call it reconstruction. That's when you connect the dots, connect the deposits and the colorimeters, and make your physics objects like electrons or tracks or jets or whatnot, or muons. And then with these physics objects you can actually make some assumptions. What was happening? Is there something? Is there a Higgs boson decaying into two photons? Is there something else happening? Is there a B quark decaying, B meson decaying into two muons? Things like that. So with some degree of purity and efficiency, we can actually select the interesting things in the software level. We have already pre-selected the events with the first level, therefore reducing the rate from 40 million times a second to roughly 100,000 times a second. So the second level, the so-called high-level trigger, that's what the HLT letters on the desk stand for, only sees these pre-selected 100,000 events per second. And it further reduces them down to 1,000. 1,000 of the best that we actually record and then further analyze. So yeah, that's the trigger system. Quite a magnificent thing.
It's screening your calls for you.
Sorry?
It's screening your calls for you.
Screening calls. So we better collect as much as we can, and that's why we're gonna collect from 2029, I believe it's now. We're gonna collect about a factor of 10 more than we are now. We are repurposing the detector and the collider as well to be able to run at higher so-called luminosity. You can imagine like more collisions in each event. So
When you record the data, do you distribute it real time?
not real time. We send them for this reconstruction, so a very precise connection of the dots that's happening on the worldwide grid. So you need what majority of the physics analysis of the data boil down to is separating between the two. And usually you've got a plenty of observables available in your collision. How many tracks are there? How many particles? What were the directions of the particles? So much data. For a human, it would be not feasible to keep in mind all of the variables at once. But if you train an AI, it can find the correlations and it can optimize the separation between your events. That's something we use very often. So that would be another.
So it's a new era, basically.
We are, I mean, we've been using this even before the currents.